Now, having done an example with finding extreme values using critical points and the second derivative test, we need to remember that back in single variable calculus there was this alternative idea of classifying extreme values called the closed interval method. And really the idea here was to say, well, if we wanted to find an absolute min and max of a function on an interval that was restricted to us, what we could do was say, okay, well, we can still find the critical points, so we do f prime, and then what do we get? 3x squared minus 3 is equal to 0, and then we have to, of course, solve and whatnot. We get x is plus and minus 1, but then we say, okay, well, we chuck out negative 1 because it's not in our interval, so then we have this list of values where we do where we have the x value and f value of, okay, we have to check the endpoints, and then we also have to check our critical points, and what we end up with is, if we evaluate this, we get 0, minus 2, and 18, and then what we said was that, okay, well, the most negative, that was going to be where we have an absolute min, and then the largest of these is going to be where we have an absolute max. And this idea is the closed interval method. So does there exist some multivariable parallel to this idea? And the answer is, well, we'll get to it. But we were able to say this because we had a continuous function on a closed interval, and when that happens, we said it will attain an absolute max and a minimum. Absolute min, and absolute max, okay? So does this extend? And, well, maybe, but I think the bigger idea is that, well, we were on a closed interval, so it would be a really good idea if we checked our boundary. And so if we did this, I think that might be enlightening. Just for notation purposes, for a particular region, if we use S as the region of interest, then we're going to call del S its boundary. Okay, that's just a notation that we use at this level. Okay, so then here we have an example where we want to find the minimum and maximum values of a certain function on a certain domain. And so if we just visualize that domain, it is going to be what we think of as the unit disk, right? Because we have radius 1 centered from the origin, and we're looking at everything on the interior part. Okay, so we're looking at that in the xy plane, and then looking at how that restricts our three-dimensional surface. Okay. Well, we can go ahead and proceed per normal. Just as we did in single variable, we could, look at the gradient, or look at that derivative matrix, and say, okay, well, the gradient is just going to be 2x and then minus 2y, and then we get a critical point just at the 0 vector. Okay, that's kind of basic, fine for right now. And so then I look at the Hessian, and that's going to be 2, 0, 0, minus 2, and here we can say, okay, well, this is going to be the sequence of determinants, even without plugging in our critical value, is going to be plus and then minus, and this is going to be indefinite, and so then any point that we get is going to be a saddle point. Okay, so we know that 0 is a saddle point, but what about everything else, right? So we're restricting this surface to be within this sector of the xy plane, and so we need to look at that boundary, right? So let's look at the boundary. Okay, so we're going to look at the boundary, or del D. Okay, and well, we know that the boundary here is just the unit circle. Okay, and from our previous studies, we can parameterize this right? We can parameterize this as cosine t and then sine t, such that t lives in the region, or in the interval 0 to 2 pi. Okay, and then this is fine, but when I look at f restricted to just the boundary of our region, well, that's going to be the same as saying, well, f is no longer of x, but it's of cosine t comma sine t. Okay, and when I do this, I get cosine squared t minus sine squared t. Okay, and what I need to do with this now is optimize on that closed interval. So this is redoing that Calc 1 problem, where we have to find the critical points, the mins and maxes. Okay, fine. And this, I encourage you to pause the video and do it for yourself. What we end up getting is that we get the maxima occur at t is equal to 0 and pi. Okay, so then what this is going to correspond to is the points 1, 0 and -1, 0. Okay, and then when we find these, what we end up getting is that f is 1. Okay, and then similarly we can repeat that procedure for the minima rather, and we get t is pi half and 3 pi halves. And so then these are going to correspond again on the unit circle to the points 0, 1 and 0, -1. And then when we substitute these in, we get that f is -1. Okay? And so what I encourage you to do at this point is look at the make a graph of this surface in GeoGebra, and I couldn't find a way to restrict it just to be on the unit circle. If I figure out a way, I'll show you in class on Wednesday. Otherwise, imagine restricting it to this, and my bigger question is, can you identify these maxima and minima on a graph? And just to recap, what we did is we said, okay, well, via the closed interval method idea from Calc 1, we had to find our critical points via our standard method of gradient, classified by the Hessian. We got a saddle point, that's boring. Then we looked at our boundary, or kind of the ends of our intervals. That's the parallel idea from Calc 1. And we were able to look at that boundary and say, oh, well, it's a unit circle, parameterize, and solve that, I guess, put in that parameterization and see what we got, and optimize it. So that is to say, find the derivative, find where the maximum values, or I guess, find the derivative, critical points, classify the critical points, all that stuff. So it's kind of 2 optimization problems in one, and we got everything we needed from there by finding the maxes and mins, translating that back to f. Okay, so kind of in a nutshell, what that closed interval method idea was from Calc 1 and how it extends into multivariable calculus. We will formalize this idea in the next video.